Welcome to the Akka Streams in Action talk. And there's also Reactive Streams in there, but it's smaller font and also not smaller meaning, but smaller the thing that you'll actually see, right? Because we'll actually be looking at Akka Streams, which is a implementation of Reactive Streams. So many things that it does originate from the Reactive Streams initiative, but we'll be looking at Akka Streams today. So I'm Konrad, Ktoso, if you ever wondered how to pronounce that. And I'm on the Akka team at Lightband currently. So other community things I run in Krakow, notably the Geekon conference, if you ever want to visit Krakow. And yeah, just a slide about Akka. But today we'll actually build stuff. There will be a bunch of examples, which is finally some code in my talks, because my previous talks were mostly slides and explaining concepts. But today we'll use unreleased stuff because it's Scala Days, so why not? Few of the features that we'll be talking about are either released as a milestone and may still change a bit, or are not merged pull requests, but I'll specifically highlight that. And the reason I'm talking about these things because kind of the road ahead is really exciting for Akka Streams. So why not show exactly what we're up about in the near future. So stream. The word stream is the most abused word like in all the libraries recently. Like everything is a stream and everyone defines stream as a different thing. Like, what is actually a stream? So let's look at what we mean in Akka Streams when we talk about streams. And people keep using waterfalls when they talk about streams because it's lots of nice pictures of waterfalls, but actually I thought that it's not really just a random waterfall that I want to talk about. It's a dam because it's a controlled flow of data. It's not just random amounts of data coming in and through. We actually do control the rate to be exactly the rate that we want to have of flow of data. So that's pretty much the Reactive Streams movement. It's about processing data at exactly the rate we want to and not faster because we might blow up. So before we dive into actual code, I promise you there will be plenty. I do want to give a super short story so we actually know where this all came from. So yeah, reactive extensions, 2009-ish in .NET, right? They did introduce them for the .NET platform back then. But fast forward to 2013, and then kind of reactive programming is a thing already, right? It's widely known. And we have a bunch of implementation, a bunch of libraries which solve different problems, but things start to slowly converge. So Play had iteratees because they wanted to have this back-pressured way of exposing this lazy stream of data. Akka solved at that time just the I/O bits, and it also had back pressure, but it was a negative acknowledgement based. And then Ben started working on RxJava. His reason for working on RxJava, which is basically a port of the concepts from .NET, was that they wanted to build some asynchronous processing, and kind of he needed a nice API to actually convince the rest of the teams to actually use that. So we had this situation that, okay, everybody solved parts of the problem. So Play had a pull-based backpressure with iteratees, which came from Haskell. A bit difficult to use, I would say. Akka had, well, the low-level bits, right? That's what we were doing, and still have in Akka I/O. And RxJava focused more on the nice API side of things, right? It's the nice fluent APIs we know and love, similar to the Scala collections, but not the same. Here is an iteratee if you never wrote one. And the biggest problem about it is just by glancing at it, you're not quite sure how would I use it. But I don't mean to bash it, just saying that that's the reason I do think iteratees are going, out. So people meet, so Roland meets Eric, Victor meets Marius, and suddenly things start to converge that we all seem to kind of be looking for a similar concept, which then gets termed as, coined as reactive non-blocking asynchronous backpressure, which is a mouthful, but actually is these goals. So it has to be asynchronous, right? We want to do reactive programming, has to be asynchronous. We obviously don't want to be forced by the APIs to block, obvious, and it has to be safe, which is a key feature. So it never should allow the library to overflow the subscribers of your data. Like, that's the goal of the library, of this Reactive Streams movement. And then, yes, it should allow synchronous implementations if you want to be really fast and go through an array, right? So, and then other people join the project, so the Reactive project appears at that point, and then many, many more people, including Doug Lee, and more people from the Akka and Spray team joined the discussions. I appeared and did the TCK there, so we have a TCK. And finally, 2015 gets proposed and merged into the JEP 266, which is concurrency updates for JDK9. So we'll see. Hopefully we will have it as a standard Java thing. So this is how the interfaces look like, and this is the last moment during this talk when we look at Reactive Streams. Because kind of misleading, and I've committed this sin myself of showing this slide, and then people think, oh my god, it's so simple. It both is and isn't at the same time. So the concept and the kind of division of responsibilities is pretty simple, and the number of methods is also pretty simple. Right? Here's just an onNext, so you get the onNext call if you have an element there, you just call the onNext, and you call the request if you're ready to consume more elements from the other side, right? Simple. Now the problem is, at some point people forgot the second point about Reactive Streams, which is that it's interop interfaces. It's not really meant for, if I'm doing my day job, I shouldn't be really implementing Reactive Streams directly. And why shouldn't you be doing that? Because this is the slide that never appeared in all of these talks, which is all the actual rules that these interactions in Reactive Streams have to follow, because it is a concurrency protocol, basically. So the interfaces are very simple, but you really don't want to spend your day implementing the entire thing again and again. So this is why Akka Streams is there to help you, because it's actually kind of hard to implement a correct publisher, and a correct processor is even harder. So this is why Akka Streams. So we have Reactive Streams, we all talk about Reactive Streams, they do this thing, but you really shouldn't be directly using them. You could be exposing them if you're a library, because then everybody can consume them, independently of which library they like. So, another question that often appears is, should we deprecate all our actor code and go to streams? People ask me that, and no, the answer is no, absolutely not, because they solve different problems, right? So streams complement actors, and there are situations where, like Martin's principle of least power, and Runar was talking about it as well on a other conference. So you want to pick the tool that is least powerful for the job, but allows you to get the job done. So, okay, we have futures. So futures are, okay, they're for a single element, asynchronous processing, but we didn't have an abstraction for a local, asynchronously produced, lazy stream of data. Now we have, which is Akka Streams. So if you look at it this way, so we have these local abstractions, single value, also has some transformation capabilities, but not that much. Then you have streams, which allow for streaming data in a back-pressured fashion, but they don't solve the distribution part, right? And then we have actors which actually do solve distribution. And here on this spectrum, I kind of did want to mention Akka typed, because it's still going, Roland is hacking on it. And it kind of adds more limitations, right? So if you think about it, it adds more constraints, and the constraints are actually good for you because you can't do the wrong thing, right? So it's this trade-off of power versus constraints. And then Akka actors, which are very unconstrained and very powerful. Okay, so finally going into some code, and the rest will be a bit topic jumping, but all connected to streams. So I do want to show actually the problem that Reactive Streams solve. So let's dive into some code. Yeah, basically I'm trying to show you guys the overflowing a downstream processor of data, right? So let's see how you could actually see that in your application. Because just talking about it is one thing, but actually seeing is, whoop. Okay. Nope, that's the wrong code base. That's just the Akka code base. That's the code base. Good. Okay. So let's say you have this really bad thing, so don't ever do this, okay? Please. But let's say you have this slow echo actor, and it's just replying to messages, and then you have a fast sender, and it's basically just sending a lot of messages to this other guy. As simple as that, and this slow guy is called slow, the fast guy is called a sender, and let's see how we could actually see that, yes, we're overwhelming the downstream guy because he's really slow at processing the hello messages, right? And which app is it? Slow actor app. So step 1, number 5. So, is the font big enough? Okay. So, I'm using reactive monitoring here with a console logger. You can use any kind of logging you want for it, including statsd and other things. But I just want to show that here's the mailbox size of this slow guy, and this will be printed every 5 seconds or so. And you will see that the sender, well, it doesn't have anything in the inbox. It's just pushing out the data, right? And the downstream is completely overwhelmed, and it will take quite some time until it gets through all of these messages because it's so slow. So what we would like to do is not allow for such a situation to even happen. So, here's a spoiler. We'll loop back to that. Okay, so I've shown the problem. Now let's talk about streams, and then we'll see how this actually solves the problem that I've demonstrated. Okay, so let's finally talk about streams. So, another difference from the Akka Streams implementation and other libraries of similar style is that we have this materialization phase, which comes from the fact that we have this lifted representation, right? So when you write anything in Akka Streams, so let's say you write a source single map, that's actually just constructing this blueprint, right? So all the flow, sync, sources, etc., they just construct how the thing looks like and what is connected to what. And then, once you actually materialize it, it gets converted to an actual engine that can run the thing. And here, something that may have slipped your when reading the docs, we do actually fusing. So operators that, for example, you have five map steps, they will be actually currently synchronously executed because, 5 map steps doesn't make much sense to make them asynchronous unless you actually know that one of the steps is, for example, very intensive in some way, and then you can just slap a asynchronous boundary there. So we have this materialization step, so it takes the blueprint into the actual engine, let's put it this way. So it does fusing, and we can do other optimizations because we have the entire layout there, we can look at it. And then we actually run it. And all the asynchronous communication, of course, is actor-based, as you would expect. And where does the synchronous boundary actually comes from? It comes from either if a stage has defined that it needs a separate dispatcher. For example, if you're using file I/O to just stream a CSV into Akka Streams, it by default has a dedicated I/O dispatcher, and it will be running on that dispatcher, so it's file access. So you want it separated from the rest of the stream. So that's one way you can get a asynchronous boundary somewhere. Another way is to explicitly say .async, and then that part of the pipeline is basically put into a separate actor. And then you run it. The key feature here is that this is really transparent. You don't need to design up front where the boundary will be. You just write your thing, and then you think about, oh yeah, this should be isolated, or this should be async, and then you can put in the boundary. So, like I said, a bit of topic jumping, but also, I think, topics that are a bit misunderstood in the community right now. So let's continue with the custom stages thing, because it's also a key feature that isn't that noticeable unless you know where to look. That it is a feature. So we have this concept of flow. So flow is a thing comes in, a thing comes out. Easy, right? And it's basically a black box. If you look at it from the outside, it could be a map stage, it could be a filter stage, easy. So we have a lot of pre-implemented, very generic operations. All of them are defined on flow-ups. So that's the first place you should be looking for operations, if you're looking for any. But let's look at what it actually is. So we have this thing called the flow shape. And now let's look into the black box. Okay? This is not something you need to do very often, but I would like to explain to you guys how it actually differs from all of the other libraries, because this kind of sets us apart. So we have a flow shape, and a shape basically means that you have does this work? Kind of. Okay. So you have an inlet and you have an outlet, right? Which is a flow. One thing in, one thing out. So it's still a flow, and it has the logic inside, right? It could be this mapping function. However, the general concept of shapes is arbitrary shapes. You can do anything. So if you would add another inlet, then you suddenly have a merge-like structure, right? And it's still, everything is expressed in the same shape concept. So, and then if you look at the APIs, it surfaces. So this is why I'm saying that you probably didn't notice this, but it's actually surfacing in here. So we have, for example, source from graph, and you can go via anything that has a flow shape. Usually it's a flow, but maybe you wrote your own thing, or someone provided a library that is a flow, and you can just go through that, and it just works. So, and the key feature here is that any kind of extending Akka Streams feels native, because everything has the same concepts, and it's very easily composable and extendable in that sense. So, before I show how to write a custom stage, I do want to tell, usually you don't have to write a custom stage. Usually you can just get away with the normal operators, and if you want to go really powerful, the most powerful operator we have for these things is probably the stateful map concat, so it can have state, like an accumulator, for example, if it's counting things. But let's see a very simple 100ify. Okay, so let's say I have this very simple Akka stream. Actually, did anyone not see Akka Streams before today? Okay, so that's Akka Streams. Very simple to read, I would think. So you start from a source. It has a single random tweet value. Then I just extract the name from it. And map concat is like flat map. So we emit a iterator here, or iterable, and then it flattens it out into the stream, right? But let's say that I want to implement such an operation. So it's as simple as via and something that has this shape. And like I said, it's just a graph stage that extends this shape. It has this inlet and outlet. And now maybe you'll notice, oh, even in the internals, these things are typed, right? So another difference from Akka actors is that we're actually very, very typed in Akka Streams. And then you set how the input should be handled. And it's as simple as, okay, if someone pushes data here, I grab the element, and then I decide what to do, right? The thing I'm trying to highlight here is you're not implementing the Reactive Streams interfaces here, because they have these many, many rules how they should behave about cancellation, error handling, and all the fuzzy things. So all the fuzzy things are handled for you, and even if you go low level, because that's like the lowest of the low levels, if you want to implement custom things, you're still guarded from complexity. But also let's show the usual way how you would implement custom things. Custom things can be very easily implemented by composing existing things, right? So rather than going graph stage like right away into the lowest low level, as you can see here, many of our stages are just implemented in terms of other operations. Stateful map concat is a popular one. And here we have some custom ones, actually. Okay. So, let's talk about Akka HTTP, right? So Akka HTTP, it was developed, as you well know, kind of together with Akka Streams. It had the same release cycle, and it was also one of the driving users of Akka Streams, at least for us. So where did we end up with that? So Obviously, an HTTP server is this flow of HTTP requests to responses, but that's not where it ends, because that's still easily representable as a function, like, for example, Finagle does. But where it really starts shining is that it's actually, through all the layers, it's the same concept of this streaming data. So for example, an HTTP entity is a source of byte strings, right? So you're reading in the byte strings as they come in from the client, for example. And also, WebSockets, again, everything is a flow, and everything composes as nicely. So let's see how that works in action. And this is that part that hasn't been merged yet, because still polishing the pull request a bit. And I'll show exactly which part isn't once IntelliJ unfreezes. What? Oh, come on. Oh, that's silly. Oh. Sorry about that. Do we have IntelliJ people in the room? Please fix that. And I need the presentation mode. Yes? Okay. Back to our source, Akka, HTTP. Okay. So, the one part that isn't merged right now is basically this trait. So it's called the framed entity streaming, and it's a feature that allows you, for example, someone is uploading a CSV file, and you want to consume it line by line, or a JSON thing, and you want to consume it object by object, then you can just use the unmarshalling infrastructure, which works like that. So, before we go into that feature that isn't merged, let's talk about the basics, which is the extract data bytes, which is a directive that helps you to extract from an incoming request. You can get the raw data bytes that someone is uploading, maybe in a post request, right? And in this part, I'm just summing how much data there was, right? So because this data bytes is a source of byte string, I can just run a fold operation on it and add all the sizes of the chunks. And then once it completes, I complete with total length in bytes. Very simple. And that's going to be marshaled as a plain text response. And maybe just to show another lower level where this all comes from, extract. So extract is the general purpose. You can get things out of context, and then I extract the request. And what is the request? It's the HTTP request. What does it have? It has an entity. Okay. What does the entity have? Well, it has the data bytes. So if you think about how it matches with HTTP concepts, it's very directly represented in that sense. So let's run this for now, and then we'll run the more fun bit. Here below, I have I'm just posting some tweets. I can show you the tweets maybe. So it's just a line-by-line JSON object, and we'll get to why that's actually maybe sometimes useful. But for now, let's run the thing. And we post to the step 3 raw endpoint. Okay, it counted the thing. Maybe exciting, maybe not that much. Here you can see it better. But the next one is already the exciting feature. So let's say I have the entity, and usually you could say I want the entity as a tweet, and then we unmarshal the entire entity as a tweet. But what if it's a incoming like stream of metrics from some IoT devices or something like that? Imagine these scenarios. So you want the source. So you can say as source, and that's the unmerged thing. And then you get back not the raw data bytes, but actually a source of tweet. And how do we handle that? Well, basically, in my JSON protocol, we need to detect the framing somehow, right? You need to know which part of the byte string should I unmarshal as the actual object, right? So for JSON, there's multiple ways to do it, but basically the safest one is bracket counting. Natty recently also did the same thing, which I found funny because I was really hoping there's a better way, but no. So basically you have a bracket counting framing, and framing is also a concept available just in Akka Streams. So you have framing. And the default ones that we provide in Akka Streams are very generic. So it's delimiter-based or length-based, right? And then we provided this specific one in Akka HTTP that's for JSON. And CSV is very simple because you just, on the new line, you split, right? So I have a source of tweets, and these tweets have a sentiment score inside, something like that. So instead of summing the bytes, I'm summing the sentiment. And let's see if it actually works. The endpoint is framed. Yeah, and it's summed and unmarshaled the stream, pulling in as fast as the server can consume it, and not faster. And then again, we have the other way. So you can just expose a Akka stream to HTTP. So here we have just a source of random tweets, and we just complete with it, which was something I saw yesterday. I do have to show this to you guys. I don't have them. So the IntelliJ guys were showing me yesterday a feature called Explain Scala. You should check it out, because here we have some implicit conversions, right? It handles the conversion from the Akka stream to an actual HTTP response, right? So there's some implicits involved. People were always complaining about the marshalling logic and spray and Akka HTTP being very, very fuzzy, and the feature that the guys showed me yesterday basically explains exactly what is happening here. So, but it's in a nightly build. So, pretty simple. But instead of showing this one, I want to show the WebSockets one, because now we're going into the integration land, how if everything is a stream, we can easily connect them together. So, if a WebSocket is a flow, we have some incoming side and we have some outgoing side. So the incoming side in this one, I don't really care about that much. So I'm just ignoring the incoming data. So the client is sending me a WebSocket request. I'm ignoring it because this endpoint is basically just streaming data from Kafka. There's a Kafka topic, and how is it implemented? We'll see in a second. But basically, it's a source, and as you know in Kafka, you need to commit if you read the thing, or auto-commit. But that's the next slide, so we'll talk about it in a second. Now let's show the socket. And here at the bottom, maybe you see, I'm just connecting a Kafka console producer. So whatever I write here goes into the topic, then through Akka Streams it pulls things from the topic, pushes it into the WebSocket, and the WebSocket gets consumed by a client application that's also Akka Streams. Here's the client, and we're basically sending a single WebSocket text message there, right? Single WebSocket request with the client flow, and the client flow prints all the incoming data, and it emits only one single request, which in this example is ignored by the server anyway. So, we want to run the client. 4. And then I went to, what? Was not found, what? Okay, let's try again. The app, here the client. As you see, typed in some data into the Kafka producer, went through the topic, and just connected all the way through to the WebSocket here. So I got back text messages. So the kind of feature here is that it's really easy to take together all these streaming libraries and they just fit. Okay, so where else does it fit? Because we're kind of going into this area of more and more things want to integrate, right? And of course, we should also integrate streams with existing like parts of Akka. Here, the query side long requested feature for Akka persistence, which is basically more like a data pump. Still experimental, we're working on perfecting the APIs still, but the key here is that it's also a stream. Right? So the query side is you have the persistent actors, they are writing some data, and on the query side you want to get out this exact data and maybe put it into a other format or query optimized store. So it's not precisely the thing you would be directly using to query the thing, but it's more like a data pump that you would put into a optimized storage. Important to remember about, in general, CQRS architectures. So who supports this already? Well, the Cassandra plugin, which we maintain nowadays, does support it. The LevelDB, which is a bit toyish, but if you want to just try it out, and I'll be trying it out here with LevelDB, also supports it. And then two of the community plugins I know that they support it, which is the JDBC and Mongo plugins. They support it by polling. And likely more that I forgot about. So if your plugin isn't here, just tell me. We need to update the list. So how does that look like? So let's say you have a persistent actor. Anyone not seen Akka persistence before? Good, okay. Many people have, many didn't, a few didn't. So Akka persistence is basically a way of building event-sourced applications. So it adds persistence to your actors in the sense of you have incoming commands, and then you can store a event. And when this actor restarts, it can replay all the events from the past, so it can recover the same state. So here we are just telling it who it should greet. It persists a greeting, and once it has successfully persisted the greeting, it both prints a logline and replies with a greeting to whoever asked for the greeting. Right? Here, if you haven't seen Akka persistence before, you may be scared that, this looks like an asynchronous operation. It actually is, and in those, usually accessing the sender isn't safe, like in futures, right? But in Akka persistence, we take care of that, and the sender here is actually the correct sender, even though this is a asynchronous callback. So, just a nice small thing we added there. So, where is my persistence query? So what I'm doing is periodically I'm emitting some names that should be persisted and greeted. And here's the query side. So the right side is basically just an actor. The outside world doesn't know that it's a persistent actor. It's just a normal actor ref, right? That's a good thing, that you don't have to care about how the actor is implemented. And here, the query side is as simple as you get a query journal for whatever journal you're using. And here, we have this journal, which exposes APIs like, give me all persistence IDs. And the type is, well, the IDs are strings, right? And here the difference between the two APIs. IntelliJ doesn't like me today. So there's always two styles of these API calls. One is current persistence IDs, which is the stream will actually complete once it gets to the, okay, I've seen all of persistence IDs, I will complete the stream. And the other one is all persistence IDs, which will keep the stream alive, and it will, depending on database, it may have to do polling or it can subscribe to something. And that will keep the stream alive, and if new persistent actors come into the system, the persistence IDs would be picked up here, and you can basically react to well, live events in that sense. So here, let's doesn't matter that much. Let's use all, and then we have the ID, and then for the ID, I can query all the events, right? So here I can just extract the events that this actor has persisted. Usually, this would be on a probably different application, not right next to each other, right? So let's run this thing. And what's the name here? Step 4. Step 4. Okay. And as you can see, it's storing the greetings. And then we should also see this event equals. And we're not. I will not maybe dwell on it. Should have printed the thing. Well, so the Kafka sources and sinks that I showed a while ago are actually a cooperation and have been started as Reactive Kafka by Krzysiek Ciesielski and Adam Waski from Software Mill. And it's a project that we're currently cooperating together and polishing it so it really is nailing the thing. And an interesting thing from that is that, yeah, the acknowledgements, right? And you will notice that in many situations you will need some kind of acknowledgement in these stream processing situations. And the idea here is that we are experimenting with APIs specifically on the Kafka case, but it's a general thing. And once we have APIs nailed, we can, for example, extract a hackable type that maybe has some support, or it's just the common type, that if you need this thing, then libraries can require you to give them an hackable. And if there's a shared type, and everybody agrees on using that type, again, we have composability across libraries, if we can agree how we want to do acknowledgements. So that's the way forward with that part. And of course, the question comes up, okay, so Kafka, Akka, is it directly competing? Yes, no, especially that now there's Kafka Streams. Again, another library with stream in the name. The answer is I don't think so. I think we complement each other very, very well. And usual architectures that we see are mostly structured as Akka being the actually take traffic take on the traffic, do some transformations there, do some actual logic there. Kafka being more like the buffer that you want to offload the maybe pre-processed data for later processing, and then you both consume it in Akka Streams. If you want to, maybe do some more side-effecting things, like send the customer an email that, hey, now you have reached a quota and you can get a promotion or something like that. So it's more for these things, and it's arbitrary. Whatever you need to do, you can do in an Akka app. And then, of course, for more data science-heavy applications, we do think that Spark is really great for that and just fits. So it's not that we're competing with these technologies, we're integrating with them. Right? And of course, the back pressure is all the way through. So here's the, looping back to the first example I had today, which is, okay, we had this actor case that we're overwhelming this actor, and this wasn't too bad. I mean, nothing blew up, but if you have many, many actors and you don't control the rates of how you're processing, then you sometimes can go into just too much GC and problems like that. So let's see how we can solve that with just using a stream for that. Oh, maybe this slide more. So let's say I have actors on both ends of the stream because I'm integrating with something existing. And in the stream processing, I'm doing some transformations, right? Usual. Then we have, for both sides, two ways to integrate there. So because the reason is, in an asynchronous message send, you don't have a blocking way to directly tell, hey, please stop sending. It would be asynchronous anyway, right? So it would be an ACK. So there's two APIs. One of them is a queue that has a bounded limit, and if you try to insert into it and it's overflowing, it will tell you then. And the actorref, which will, for example, start dropping. On the other side, we have actorref if ACK, which is basically pulling, in a sense, because if it doesn't acknowledge a message, we don't send more messages to it. And then we have the actorref sync, which we just keep pushing as fast as we can data to the downstream actor. Okay, actors and streams. Actually, we can loop back to the step 1. Okay. So here we said loop back. So here we have a source. We're repeating the hello message, and we're using this actor ref with Akka. And let me explain the types here. Because if you want to integrate safely so we don't overwhelm the downstream actor, we want to know if it's ready to consume more elements or not, right? So it's a very, very simplified version of a work pulling. It's just acking. So here the message types are, because we want to tell the actor that, okay, now we're starting, you will be getting messages. Here's the ack message, so the message that we expect that we get back from the actor, and then we see, okay, it has acknowledged, we can send more data. And we also have another message that we send from the stream to the actor once the stream has completed. The actor here is very simple. It's being slow. Remember, don't do that. And then it replies with a OK. So that's the acknowledgement. So let's run the same thing as previously, but now with a stream feeding the data into it. You could imagine this being maybe exactly consuming from Kafka, and you want to feed from Kafka into your actor application, but not as fast as possible, but not faster. And then number 5. And we'll see some metrics. Okay, mailbox size. We see there was 92 times we measured the thing, and from that we see the distribution of the mailbox size. Yeah, it's basically always 1, because here we're acknowledging, then we get a message, acknowledging, then we get a message. Slower, but not overwhelming the actor, right? Good. So, in general, I think it's exciting times in terms of actually putting Akka Streams to use and integrating it with various other both libraries and concepts and building on top of it, because now the APIs are stable and we're confident in this is the thing we wanted to build. And yeah, many of the next steps for us are really related to Akka Streams. For example, many of you noticed maybe that we're rewriting the remoting currently, the goal being this mostly to speed it up, have it also more maintainable and more introspectable. And well, of course, it's based on Akka Streams, because we found the work there is just much more pleasant this way. Then we'll do some other work, like here I mentioned the reactive Kafka work with software mill. It's currently in milestone phase, so don't treat this as an announcement, because we're still working on the APIs there. But there will be a nice announcement, and thank you to the software mill guys who've really helped us with that one. And we'll see. And here's an announcement that there will be an announcement. And I'm sorry because I wanted to announce the actual thing, but we really want more contributors kind of to join the efforts, because why not? And we thought that maybe a mini competition or something like that will be fun, and we also want to spend some more time and resources on helping people to contribute to Akka, to be even more inclusive as previously. So have your eyes peeled for that, and if you want to just start hacking right away, here's how. There's easy to contribute and nice to have tags on GitHub. Those are nice tickets to start out with. There's, if you want to hack around with crazy stages, so you can contribute to the Akka Stream contrib library, which is more accepting in various crazy stages than the core Akka, because it's a contrib thing. It can move faster. And then we're on chat and mailing lists, so find us there. So thank you. I hope it was okay. And if you have any questions. So we have maybe a minute or two for questions. Very in the middle, maybe. Person in blue shirt.
Hi. How to be able to gracefully shut down a streaming application, so that, for example, you can roll out a new version of it, but you want to only upgrade when you know that at least everything it started picking up, is being handled before you shut it down, right?
I'm having trouble hearing you, actually.
how to gracefully shut down a streaming application so you can roll out a new version.
Gracefully shut down streaming applications.
Yes.
So I kind of played at the point of Akka Streams being, it's like a super powerful iterator, right? So yeah, streaming applications, but all kinds of, it's not that the stream kind of changes the way you've been building applications really, because if you had a message-based application with actors, the same concepts apply to versioning the messages and having them compatible as with a, for example, streaming app. So I don't think it changes much in that sense. You need to care about message versioning. Here you need to care about element, which actually is a message anyway, versioning. I don't know if that helps, but that's my answer here. Do we have a last question, or are we happy? Okay, so let's have lunch. Thank you very much.